Short circuit level is the amount of current that flows on the system during a fault. These faults can be caused by a lightning strike, weather conditions, or equipment failure. During the fault, the system can see a direct connection to the earth and current flows from all sources into it. SCL is vital during such a fault as it helps us to maintain system voltage. The short circuit level SCL is the amount of current that flows on the electricity system during a fault such as those caused by lightning strikes, other weather conditions, or equipment failure. This is also referred to as the fault current. When a short circuit occurs, the voltage at fault point is reduced to zero and current of abnormally high magnitude flows through the network to the point of fault. If we get a disturbance, then a stronger system will dampen it out quickly. It's just the same as how a strong bridge with reinforced joints would wobble but settle quickly when placed under force. If we operate a system with low SCL, it may take longer to recover after a disturbance. Large coal and gas generation create 5 times more fault current compared to wind and solar. A 100 megawatts generation would provide in the region of 500 to 700 MVA of short circuit level. Wind farms are limited by the rating their electronic component, so the same level of generation may provide only around 100 MVA of SCL. Now, higher proportion of generation around the world come from renewable generation, which, as we've stated above, means there is less SCL on the system. In turn, the low amount of SCL can create operability challenges. The reason for this is that when there is a low amount of SCL, any voltage change causes a bigger disturbance which travels further. If left unmanaged, these disturbances could trip generation or make the whole system go unstable, which would damage equipment. Short-circuit currents are currents that introduce large amounts of destructive energy in the forms of heat and magnetic force into a power system. A short circuit is sometimes called a fault. It is a specific kind of current that introduces a large amount of energy into a power system. It can be in the form of heat or in the form of magnetic force. Basically, it is a low-resistance path of energy that skips part of a circuit and causes the bypassed part of the circuit to stop working. The reliability and safety of electric power distribution systems depend on accurate and thorough knowledge of short-circuit fault currents that can be present, and on the ability of protective devices to satisfactorily interrupt these currents. Knowledge of the computational methods of power system analysis is essential to engineers responsible for planning, design, operation, and troubleshooting of distribution systems. Similarly, if SCL is too low to network protection, that open circuit to protect the system could miss that a fault is happening and leave the network in an unsafe and unstable condition. That isn't an issue as if have the expertise to safely manage an energy system with low SCL. Traditionally, system operation had the required level of SCL from all the generation that is running to meet the energy needs for any system operation. As we're now seeing a shortfall in SCL in many TSOs areas due to high penetration of renewable, we need to look to top up SCL from other sources and artificially inject SCL into the grid globally. The short circuit level, or SCL, is used as a description of the strength of the electricity system. When SCL is high, the system is said to be strong, and when the SCL is low, the system is said to be weak. System strength is a key factor. The stability of the grid when a fault occurs. When SCL is low, any voltage changes can cause larger disturbances which travel further through the system. If left unmanaged, these disturbances can trip generation and damage equipment. If SCL is too low, network protection measures, which open circuit breakers to protect the system, could miss that a fault is ongoing and leave the network in an unsafe and unstable condition. The lower the SCL is, the more likely the system is to experience significant voltage excursions, stability problems, power oscillations, or fault right-through issues following a disturbance. A power system with low system strength will exhibit one or more of the following: undamped voltage and power oscillations extending over wider areas, deeper voltage dips and higher over voltages, e.g. transients, reduced generator fault right-through, failure of protection equipment to operate correctly or at all, longer times to voltage recovery after a disturbance, instability of generator dynamic plant voltage control systems, increased harmonic distortions, a byproduct of low system strength, and higher system impedances. Impact of inverter-based technologies on electricity grids. Wind and solar PV generation and battery storage systems connect to the grid using power electronics, almost all of which are currently of the grid following inverter type. For these inverters to operate, they must follow the grid voltage waveform seen at their terminals and inject current at an angle that follows the measured voltage. In a process known as a phase-locked loop, the inverter creates a synchronous clock driven by the voltage phase angle it senses from the grid. This process is disrupted when there is a fault on the grid because the voltage waveform becomes unstable. After the fault is cleared, the inverter must relock onto the grid quickly to ensure stable control. If the system strength is low, the phase angle change between the pre-fault condition to fault clearance will be larger than on stronger systems, making this process significantly more difficult. If the voltage phase angle detected by an inverter is inaccurate, the current will be injected incorrectly, adversely impacting the voltage waveform of the grid, which in turn increases the current injection error, potentially creating a cascading impact with widespread disruption to the grid if not corrected. Therefore, not only do inverter-based technologies make minimal contribution to system strength, they create additional weakness in the event of a fault. The more inverter-based devices that are connected in close proximity to each other, the greater the system strength needs to be at that location in order to maintain grid stability, as there is a higher potential for them to influence grid voltage. A short-circuit analysis is used to determine the magnitude of short-circuit current the system is capable of producing, and compares that magnitude with the interrupting rating of the overcurrent protective device's OCPD. Since the interrupting ratings are based by the standards, the methods used in conducting a short-circuit analysis must conform to the procedures which the standard-making organizations specify for this purpose. The American National Standards Institute (ANSI) publishes both the standards for equipment and the application guides, which describes the calculation methods. Short-circuit currents impose the most serious general hazard to power distribution system components and are the prime concerns in developing and applying protection systems. Fortunately, short-circuit currents are relatively easy to calculate. The application of 3 or 4 fundamental concepts of circuit analysis will derive the basic nature of short-circuit currents. These concepts will be stated and utilized in a step-by-step development. The 3-phase bolted short-circuit currents are the basic reference quantities in a system study. In all cases, knowledge of the 3-phase bolted fault value is wanted and needs to be singled out for independent treatment. This will set the pattern to be used in other cases. A device that interrupts short-circuit current is a device connected into an electric circuit to provide protection against excessive damage when a short circuit occurs. It provides this protection by automatically interrupting the large value of current flow, so the device should be rated to interrupt and stop the flow of fault current without damage to the overcurrent protection device. The overcurrent protective device's OCPD will also provide automatic interruption of overload currents. Short-circuit calculations are required for the application and coordination of protective relays and the rating of equipment. All fault types can be simulated. Risks associated with short-circuit currents: the building facility may not be properly protected against short-circuit currents. These currents can damage or deteriorate equipment. Improperly protected short-circuit currents can injure or kill maintenance personnel. Recently, new initiatives have been taken to require facilities to properly identify these dangerous points within the power distribution of the facility. Why is a short circuit dangerous? A short circuit current can be very large. If unusually high currents exceed the capability of protective devices like fuses, circuit breakers, etc., it can result in large, rapid releases of energy in the form of heat, intense magnetic fields, and even potentially as explosions known as an arc blast. The heat can damage or destroy wiring, insulation, and electrical components. An arc blast produces a shock wave that may carry vaporized or molten metal, and can be fatal to unprotected people who are close by. Fault current calculations are necessary to properly select the type, interrupting rating, and tripping characteristics of power and lighting system circuit breakers and fuses. Results of the fault current calculations are also used to determine the required short-circuit ratings of power distribution system components, including bus transfer switches, variable speed drives, switchboards, load centers, and panel boards. In calculating the maximum fault current, it is necessary to determine the total contribution from all generators that may be paralleled and the motor contribution from induction and synchronous motors. Short-circuit analysis is performed to determine the currents that flow in a power system under fault conditions. If the short-circuit capacity of the system exceeds the capacity of the protective device, a dangerous situation exists. Since growth of a power system often results in increased available short-circuit current, The momentary and interrupting rating of new and existing equipment on the system must be checked to ensure the equipment can withstand the short-circuit energy. Fault contributions for utility sources, motors and generators are taken into consideration. A short-circuit analysis will help to ensure that personnel and equipment are protected by establishing proper interrupting ratings of protective devices, circuit breaker and fuses. If an electrical fault exceeds the interrupting rating of the protective device, the consequences can be devastating. It can be a serious threat to human life and is capable of causing injury, extensive equipment damage, and costly downtime. On large systems, short-circuit analysis is required to determine both the switchgear ratings and the relay settings. No substation equipment can be installed with knowledge of the complete short-circuit values for the entire power distribution system. The short-circuit calculations must be maintained and periodically updated to protect the equipment and CC the lives. It is not safe to assume that new equipment is properly rated. The results of a short-circuit analysis are also used to selectively coordinate electrical protective devices. Short-circuit calculation and study standards, IEC 60909 International Standard Series distinguishes 4 duty types resulting in 4 different calculated short-circuit fault currents: the initial short-circuit current IC, the peak short-circuit current IP, the breaking short-circuit current IB, the steady-state fault current IC. ANSI Standards North American Standard IEEE Standards covering short-circuit current fault calculations for low-voltage electrical systems below 1000 V, are IEEE Standard 242-1986, IEEE Standard 241-1990, IEEE Standard C37.13-1990, IEEE Standard 141-1993. IEEE standards dealing with short-circuit current calculations for medium and high-voltage electrical networks could be seen in table. Factors affecting the accuracy of short-circuit fault studies, IEEE STD.399 stated that are many some factors affecting the accuracy in a short-circuit study. They are system configuration, system impedance, neutral grounding, pre-fault system loads and shunts, mutual coupling and zero sequence, phase shifts and delta Y transformer banks. Software used for short-circuit study. Various internationally recognized software are available worldwide which can be used to perform short-circuit study for commercial and industrial facilities. The topmost, widely used ones are the following: ETAPI, SKM, Easy Power, PSS, etc. Steps in short-circuit study. General steps in a short-circuit study are as follow: data collection. Information on all the components is obtained during a field visit and then tabulated. Additional data is obtained from the electric utility, manufacturers, or calculated from field data. Single line diagram. A power system diagram shows how all components electrically connected is created, or, if one already exists, updated. Additional data needed for the study, such as cable impedance, can be obtained with information from this one-line diagram. Software analysis. Using one of the many short-circuit analysis softwares available, the system data is input and the short-circuit currents at various points in the system are calculated as output. Tabulate results. The output of the power system software is typically put into a table for comparison with the ratings of equipment in the system. If the calculated short-circuit current at a given point exceeds the short-circuit rating of the equipment installed at that point, then that location is flagged as being inadequately protected. Final report. A detailed report will describe the scope of the study, all assumptions, the origin of the data, the methods used for calculating the currents, the tabulated results, and recommendations for corrective actions are published at the conclusion of the study. Commercial software comparisons. Aspen, Advanced Systems for Power Engineering. Aspen used primarily to determine equipment ratings, fault current levels, and protection coordination on the transmission level network. Symmetist performs power systems analysis on balanced or unbalanced 3-phase, 2-phase, and single-phase systems that are operated in radial, looped or meshed configurations. The module includes voltage drop and power flow analysis, fault calculations and protective device coordination. SKM Dapper performs traditional short-circuit analysis with an integrated set of modules. The module includes design and analysis including load flow and voltage drop calculations, motor starting, demand and design load analysis, feeder, raceway, and transformer sizing. DEW has an open architecture and utilizes an integrated system models ISM. The architecture and ISM provide the developer with a mechanism to directly use the results of existing relay analyses, model parameters, and external data to create custom calculations, analyses, and reports. Power Factory offers a research version that allows the user to create custom models and control strategies as MATLAB or programmed functions. Power World is a visualization tool used to analyze the system performance under different power demand scenarios. Transmission planners, power marketers, and system operators typically use the software. PSCAD offers the ability to create custom components as well as custom control algorithms. PSLF, GE Positive Sequence Load Flow software is a full-scale program designed to perform load flow, dynamic simulation, and short-circuit analysis. Typically used by power system engineers for simulating the transfer of large blocks of power across a transmission grid. PSS SynCal software package offers time and frequency domain solutions for stability and harmonics respectively. Also includes planning and analysis of utility and industrial networks. PSSE, the power system simulator for engineering, essentially has the same system capability as PSLF, a software program. Again, this package is typically used by electrical transmission planners performing load flow, dynamic simulation, and short-circuit analysis for obtaining a reliable power system. Sim Power Systems, built on the MATLAB solution engine, Sim Power Systems offers the flexibility to create custom algorithms, interfaces, and components. Synergy performs power system analysis using detailed load modeling on radial, looped and mesh network systems comprised on multiple voltages. Question is, what is short-circuit analysis? A short-circuit analysis essentially consists of determining the steady-state solution of a linear network with balanced three-phase excitation. Such an analysis provides currents and voltages in a power system during the faulted condition. This information is needed to determine the required interrupting capacity of the circuit breakers and to design proper relaying system. To get enough information, different types of faults are simulated at different locations and the study is repeated. Normally in the short-circuit analysis, all the shunt parameters like loads, line charging admittances are neglected. Then the linear network that has to be solved comprises of transmission network, generator system and fault. By properly combining the representations of these components, we can solve the short-circuit problem. Short-circuit analysis service, support of IEC 60909, IEEE 141 ANSI 37, VD 0102 and 0103, G74, and IEC 61363 norms and methods, calculation of short-circuit currents in DC grids according to IEC 61660 and ANSI IEEE 946, superposition method, including dynamic voltage support of generators connected via power electronics, multiple fault analysis of any kind of fault including single-phase interruption, inter-circuit faults, fault sweep along lines, etc. NEPLAN short-circuit analysis is performed so that existing and new equipment ratings were sufficient to withstand the available short-circuit current. This short-circuit analysis can be done either through hand calculations or through known software like NEPLAN. Using NEPLAN we can perform short-circuit studies on electrical systems in a quick time and effective manner in 4 steps. Data collection and SLD preparation, short-circuit calculations, relay coordination studies, load flow analysis. What are bolted, arcing and ground faults? A bolted fault typically results from a manufacturing or assembly error that results in 2 conductors of different voltages being bolted together, or a source of power being directly connected bolted to ground. Since the connectors are solidly bolted there and no arc created, and the high current quickly trips a protective device limiting the damage. An arc fault is one in which the short circuit creates an arc. An arc is a flow of electricity between 2 conductors that are not in contact. The resulting intense heat can result in a fire, significant damage to the equipment, and possibly an arc flash or arc blast resulting in serious injuries. A ground fault is when electricity finds an unintended, low-resistance, path to ground. When that path goes through a human body, the resulting heat can cause serious burns, and the electrical shock can disrupt the functioning of the human heart fibrillation. What are symmetrical and asymmetrical currents? A polyphase system may experience either a symmetrical or an asymmetrical fault. A symmetrical fault current is one that affects all phases equally. If just some of the phases are affected, or the phases are affected unequally, then the fault current is asymmetrical. Symmetrical faults are relatively simple to analyze, however they account for very few actual faults. Only about 5% of faults are symmetrical. Asymmetrical faults are more difficult to analyze, but they are the more common type of fault. What are protective devices for short-circuit analysis? Protective devices are designed to detect a fault condition and shut off the electric current before there is significant damage. There are a number of different types of protective devices. The two most common are fuses and circuit breakers. Fuses and circuit breakers are used to protect an electrical circuit from an overcurrent situation, usually resulting from a short circuit, by cutting off the power supply. Fuses can only be used once. Circuit breakers may be reset and used multiple times. In addition to fuses, circuit breakers and GFIs, there are electrical protection devices that detect changes in current or voltage levels, monitor the ratio of voltage to current, provide over-voltage protection, provide under-voltage protection, detect reverse current flow, detect phase reversal. Another question is, when are short-circuit analysis needed? The first short-circuit analysis should be performed when a power system is originally designed, though this should not be the only time. These studies need to occur with any facility expansion or with the addition of any new electrical equipment such as circuit breakers or new transformers and cables. Without any new additions or changes, short-circuit studies still need to occur on a regular basis of at least every 5 to 6 years. How is short-circuit current calculated? Short-circuit calculations are required to correctly apply equipment in accordance with NEC and ANSI standards. Depending on the size and utility connection, the amount of detail required to perform these calculations can vary greatly. Switches, fuses, and breakers that need to interrupt or close into a fault are of special concern. Cables and buswork also have short-circuit withstand limitations, and a thorough study will examine non-interrupting equipment, as well as switches and breakers. Standards such as ANSI C 37.010 and C 37.13 outline the recognized calculation methods for these equipment rating analyses. As the energy transition progresses, conventional synchronous generation is increasingly replaced and displaced by non-synchronous intermittent generation, which is connected to the grid using inverters. Grids around the world are seeing significant reductions of fossil fuel generation and even periods when demand is fully met by renewable generation, although not necessarily all intermittent. For example, larger hydroelectric power stations tend to be synchronous machines. Inverter-based renewables contribute very little SCL, reducing the strength and therefore stability of electricity grids, which means the ability of these grids to withstand faults is reduced. Ultimately, the ability to add more inverter-based technologies to the grid will become constrained by the need to maintain grid strength. Transmission network protection systems rely on the short-circuit level to detect faults and know when to operate. The decline in SCL means that protection measures could take longer to operate or not operate as designed, resulting in longer faults that pose a risk to network safety and stability. Historically, much of the SCL at lower voltage distribution networks has come from the transmission system, but the increase in distributed generation should see an increase in the contribution to maximum short-circuit levels within the distribution system. However, studies indicate that increasing SCL on the transmission system will be more effective for promoting transmission system stability than increases at the distribution level. Benefits of short-circuit analysis. Conducting a short-circuit analysis has the following benefits: helps avoid unplanned outages and downtime, is critical for avoiding interruptions of essential services, reduces the risk of equipment damage and fires, increases safety and protects people from injuries, determines the level and type of protective devices that are needed, provides the information needed for NEC and NFPA required labels, keeps you in compliance with NEC requirements, reduces the risk a facility could face and help avoid catastrophic losses, increases the safety and reliability of the power system and related equipment.